Hello everyone again and welcome to our machine learning tips. Today we will be looking on how we can apply the logistic regression we learned yesterday with some real world problem where we are going to be using the breast cancer Wisconsin data set from UCI Machine Learning. So as I did mention, you can always grab data set from here and try, different applications. Since logistic regression is a classification-based problem, today we'll be looking at building a machine learning model that can distinguish between different types of breast cancer, whether it belongs to the benign class or the malignant class. So you can download this data set from here, and then remember, always create a folder where you save that data set with the same location where you're going to be running your Python code or where you have your Python file saved. So when you download this data set from here, we get back to the notebook where we are going to be looking at logistic regression, how we can apply it to a real world problem. So before we go on, it's a binary class problem. As I did mention, we use it for binary class classification problems. So where we are going to be classifying, distinguishing between different types of breast cancer, which is malignant, which we are going to give it 1, and then benign class, we are going to give it what is 0. So what we are going to be looking at today, we'll be loading that data set. We are going to do some EDA. We do some pre-processing, as I did mention, like scaling it, and then we train our logistic regression model. We are going to evaluate that model. Yesterday, I did talk of the confusion metrics. From the confusion metrics, we can calculate the accuracy of that model, precision, recall, the F1 score, whatever metric we are trying to use. And then we can also try some different ways how we can interpret that model, which has to do which are the features that are very, very important. If we get back to the data set here, we can look at the different features that we have for that data down here. We have the radius, which is the mean distance from the center to points on the parameter. We have the texture, we have the parameter, the area, and so on. You can read more about this data set. So the first thing we are going to do here is, first of all, we are going to import these libraries that we use. Pandas, matplotlib. Pandas enable us to read this data. If we need to do some computation, we can use NumPy, as well as we use matplotlib for visualization, as well as the Seaborn. Then here we are going to be using this regular library for training machine learning models, which is a scikit-learn. We import the model selection where we are trying to split that data into training and testing. And then we are going to standardize the features like the values to a particular scale where we are using the standard z-score. And then we look at from the scikit-learn, we are importing linear model where we want just logistic regression, not linear regression, because it's a classification problems. And then with scikit-learn.metrics, we are importing confusion metrics. This classification report will give you the evaluation like the accuracy, precision, recall, the F1 score, and so on. So first thing first, we can just copy this URL for this data, which is from here. We can copy this, and then these are the columns of that data. So we can just do pd.read underscore CSV. We pass in that URL. Header, we don't have header, and then we pass in the column names, and then we can try to look at how the data set looks like. If we run this, remember head will just give us the first few columns. This ID, this column just uniquely identifies a particular patient in this data set, and the diagnosis is the target class, which we are going to have what? M here is for malignant, which we are saying we'll give it the positive class, and benign class, we are going to give it the negative class, which is what? 0. Now, most of the times when it is a classification-based problem, I did mention yesterday about imbalanced class problems, where if there is a great discrepancy in between the binary classes, then we cannot use certain evaluation techniques, like especially accuracy. So we do this just to see how the distribution looks like. If I run this, we can see that the benign class, they are like 357 sample, and malignant, they are 212. We see that there is not a lot of discrepancy between these two classes. So definitely we can also see the distribution here if we are using this count plot, like using the Seaborn to actually look at the distribution of these classes. So when we do that, because these we are going to drop some columns in this data set, we don't need this ID, because the ID is just to uniquely identify someone, which is just a random number. So we cannot use these random numbers to view models. So most of the times we can also look in the data set, we can see that some of these values, there is a lot of discrepancy, some are in 0 point something, and then we can have some going to like 1000 something. So that is why we have to like do some pre-processing. So we have to first of all drop that ID column, and then also we need to encode what the malignant and benign class. So to do this, we have seen how we can just pull that diagnosis column, and then we'll map it onto what where we have M, we are going to give it 1 because we are using a dictionary, and then we give B, which is the benign class, we give it what, 0. And then normally before we build our model, we have to split, because a model learns the relationship between the input and the output. So we are going to first of all split that data set into what the input, which is what we call the futures in the data. So to do this, we'll just go in there and drop the diagnosis column, since we have already dropped what, the ID column, and then we are going to have those futures. Then for the target variable, which is the class, we only need what, the diagnosis column, which in that case, since we have already mapped this into malignant to be 1 and benign to be 0, we are going to have that target to be just those 2 binary classes. And then when we are done with that, what do we do next? We have to split that data. Now, when we are trying to train a model, we have to hold part of that data to actually test how the model is behaving. I did mention in previous lessons about what we call overfitting, which is a scenario where a machine learning model can learn the relationship between that input and output so well, including noise, in such a way that it performs well on the training but doesn't do well in the test set. So that is why most of the times we want to do cut that data into 70% training, and then we hold the rest forward for testing that model to see its performance on a data that it wasn't seen during the estimation of those parameters. So this is what we are doing here. We are going to just do a train test split, which is we imported this using this this library from scikit-learn, this one. And then we are going to say, since we are passing the input futures and the target, we want the test size to be what? To be 0.3, which is like 30%, and then we are doing a random split. Now this stratified sampling here, we are taking it to be Y. Now, it is very important for you to use this stratified sampling for classification problems to be equal to the class or the target variable, because now with stratified sampling, it is not biased in when it's trying to split that data into train test split. So it give it equal classes between the benign and the malignant class. So we will do this most of the times, especially when we are doing classification-based problems. Now, when we are done with that, the next thing we want to do is we try to standardize it. Standardization, as I did mention, is a normalization technique where we try to scale those values into a particular range. Why are we doing this? Because if we look at the futures in this data set, some have very high values. Look at something like 1,297 here, but here we have something which is like pretty very low. So most of the time we want to scale it to a particular scale, since I did mention that most of these linear models, they have a lot of problems with outliers. So when we do that, we can scale that data, both the training input futures and the testing input futures. Now we are always getting the input futures because that is what we use to map input onto to the target. Because the target here, remember, is a binary class problem. So when we are done with that, I just want us to look at count the target for the train to see how the distribution looks like. We can see here that the benign class, we have 250 samples, and then the malignant class is just like 148. So meaning that we have more of the benign classes, which is the negative class. We should expect this a lot, than the positive class, which is what malignant. And then for the testing set, when we train our model with this train set, we want to test to see how it is performing with unseen data that it wasn't used in estimating those parameters. When we do this, we can see that the negative class is 107, and then the positive class is just 64. So if you see that if we are adding these two, it will give us that 212, and then we add this, it is going to give us the 357. Now, when we are done with all of that, the next thing we have to do is what? To train our logistic regression model. So we'll just do log reg, which is just the name of that model. We are going to put logistic regression, which we already imported it using our scikit-learn library here. So when we are done with that, since we are training a model that maps the input to the output, we are going to just call that logistic regression model. We had feed it, which is like feeding is just like learning that relationship between the input and output. We pass in that scaled input features as well as what? The target. So when we do that, we can try to do, if I run this, you see that it will be pretty fast in training because the number of rows in that data is pretty small. And then we can do predictions. So the predictions here is just we do y predict, and then we call the name of this model that we have trained, and then we do predict. Now we are going to predict here using what? Using the test set, which has the distribution here will be having a 107 benign class, and then the malignant will just what 64. So if I run this as I did have it, we can try to print this to see what we have. If I print y underscore predict, I run this, let's see what we have. You know, we already having these predictions. You see that we have, you know, this 0 here, as I did mention, is the benign class. And then 1 here is the malignant class. So we can see here, these are the different classes that the model was able to distinguish between. Using these input features, we are able to, you know, predict whether breast cancer is what? Belonging to the benign class or the malignant class. So now when we have this, the next thing we want to do is to evaluate our model. I did mention the confusion matrix here, which looks at, you know, the relationship between the actual and the predicted value. So we will run this and try to interpret this confusion matrix. Remember, on the confusion matrix, here on the vertical we have the actual, and then on this horizontal we have what they predicted. So let's go back to the test data. Remember, we are doing this evaluation using what is test data, the test and what, and the predicted value. So when we, on the confusion matrix, remember we had 107 samples for the benign class, and then 64 samples for the malignant class. So let's come back here and look at the confusion matrix. So since the vertical is showing the actual and then the horizontal is showing the predicted, you see that out of the 107 malignant classes from the test set, the model was able to get what? To get 106 of them right. So it only got like one wrong, which we call this what? A false negative. So, and then looking at the malignant class, which was from this sample, there were 64 of them. We see that the model is capable of getting what? 60 right and only getting what? 4 wrong. So our model is not quite bad. So we will see as we move ahead on nonlinear models how we can improve on these kind of problems. We can use, when we move to decision trees, we can see that decision trees might be able to perform well on this model compared to what? Logistic regression. So also we are looking at the precision. We see here that the model is actually capable of distinguishing between what? The benign class and what? And the malignant class pretty well. We see that the precision here, the overall here, the weighted precision here, which is looking at the overall precision between the benign class and the malignant class is like 97%, which simply means that the of all the patients predicted malignant, the model actually had those tumors to be what? To be malignant, which makes a lot of sense. You know, this is meaning that even if this data was not balanced, we are still going to, this model is really making good decisions. Now, also looking at the accuracy of this model is 97%. 97% accuracy is a good accuracy, uh, which means that the model correctly identified both what? Both the benign class and the malignant class correctly, which is, is a good model. Meaning that if we end up deploying this model into production, this model will, will be good, even though it has some uh, uh, the false positive here is not high. It's just 4 out of 64. We got 60 right, and then for the false negative, we just have one sample. So, guys, that was it for this lesson today. So then, for the next lesson, we also I also try to look at the future importance, looking at which of these futures were really important in saying that, that breast cancer was belong to the benign class or the malignant class. We can see that the first future here is what texture. Uh, and then the next one is radius. We have the symmetry and so on. So in conclusion here, we actually looked at logistic regression, how it worked with a real world application where we really had a very high accuracy. Also, for the other metrics, whether it's precision, recall, and the F1 score, they were also equally very good, because we can see that our model out of 107 malignant or no benign class, it got 106 of them right, and out of 64 malignant class, it got 60 of them right. So also, the confusion metric shows very few misclassifications, which we can see here on this confusion metric. The misclassification rate is not high. And then the features that were really, really important were what? The mean radius, the mean cavity were highly, very, very influential in the prediction of what? This cancer. So this actually demonstrates how logistic regression can be applied to what? To medical diagnostic problems. So guys, keep following for more. So the next lessons we'll be looking at will be based on nonlinear models. Like we are going to start with the k-nearest neighbor. We are also going to look at decision trees, random forest, the XGBoost, and how they work most in real world applications. Thank you so much, guys.